These are the frequently asked questions for pre-calculus for section 5.1. Days 1 and 2, actually, we had to wait until we had covered everything to start doing some homework. So in exercises 5 through 8, use identities to find the value of the expression. For number 8, the first thing I noticed about this was they left the negative inside the parentheses, and we know we're not supposed to do that. So what we would do is say, hey, cotangent has odd symmetry, so I can move that negative out in front. But really, we want to go after the second portion here, because we can see we have some identity work to do. And hopefully you noticed, wait a minute, cofunctions are supposed to be pi over 2 minus theta. So this is backwards, which means we need to pull a negative 1 out of there, factor that out to make sure that that will be in the correct direction where we are taking 90 degrees and subtracting to get our cofunction. But again, tangent and cotangent are both odd, so we'll move that negative out in front. So now I look at this and I think, okay, well, the cofunction for tangent is, of course, cotangent. So this is really the negative cotangent because we're subtracting from 90 there. So we have a negative cotangent of theta, which we already know. It's 7.89. So this one was about the manipulation with the negatives, getting everything to turn around where it needed to go. Next one was number 11. Use basic identities to simplify the expression. So number 11, we have secant of y, and then we have the sine of pi over 2 minus y. Well, that's asking for the cofunction, and the cofunction for sine is going to be cosine. And then I think, okay, wait a minute, secant, that's 1 over cosine. Make them both fractions, cancel, top and bottom, and we get 1. And there it is. So the first thing you use is the fact that you have a cofunction. And then the second thing you do is notice, hey, now that I have cosine, I should rewrite secant as something with cosine and see what happens. And what happens is pretty doggone quick. All right, number 16. Number 16, when I take a look at this one, I see sine squared and cosine squared. That is a 1. 1 plus tangent squared. Whoops, I'm missing a t. Tangent squared u over secant of u. And then I start thinking, wait a minute, 1 plus tangent squared u, isn't that supposed to be one of our Pythagorean identities? And if you need to, you can always work your way through it and take your cosine squared plus sine squared equals 1 and think, okay, how does a person get tangent? Well, that's from sine divided by cosine. So I'd have to divide by cosine squared, and that's going to give me my tangent squared right here. This is going to be a 1 on the left hand side, and over on the other side I have 1 over my cosine squared, and that's going to be secant squared. So we'll have secant squared theta, which works out very nicely. When we look at our denominator, we're going to have secant squared u over secant of u. And of course, one of those is going to cancel out. And we will get secant u. Number 24 is the next one on your list. And it is 1 plus the tangent of x over 1 plus the cotangent of x. And it says simplify the expression either a constant or a basic trigonometric function. Support your result graphically. And I'm not going to do the graphically part, but I'm going to show you the identities here. So where to go with this? Well, first of all, we've got a tangent and we have a cotangent. So what I would want to do is try to get rid of that secondary trig function by changing that to 1 over tangent. But then I notice I'm going to need a common denominator if I'm going to do some work with that denominator. So we take her down a notch and say, okay, well, 1 would be tangent of x over tangent of x plus 1 over tangent of x. So my new denominator should be tangent of x plus 1 over tangent of x, okay? Well, this is my numerator. And if I'm going to divide by my new denominator, I'm going to need to flip it. So I'm going to divide, which means multiplying by the reciprocal. Which is beautiful because those buggers cancel out. And there it is. So fractions, it usually is a sign, hey, I better try and work with my denominator here, get my common denominators and see what's going to happen there. Number 25. Oh, first thing to do with number 25 is let's go ahead and distribute that negative through these parentheses. So secant squared x plus cosecant squared x minus tangent squared x minus cotangent squared x. That's a very good place to start. Now, what to do? What to do? Well, what we would want to do is figure out a way to write this so that we have all basically the same trig functions as we're going through this. So I look at secant squared x and I think, you know what? Secant squared x is 1 plus tangent squared x. So maybe I'll try that out for size. And then cosecant of x, well, that is another one of our Pythagorean identities, and that's cotangent squared x plus 1. And now I see great things are going to happen, so I know I don't have to mess with that cotangent. So all I did was take a look and say, you know what, I have two secondary functions here. Let's see what happens if I replace those with the primary, in this first case, 1 plus tangent squared x, the primary trig function. But cosecant, you know, that secondary trig function works in the Pythagorean identity with cotangent, and that was another part of this problem. So you get to this point and you realize, oh, well, lots of good stuff is going to happen here because tangent squared x minus tangent squared x is 0, and cotangent squared x minus cotangent squared x is 0, and that's gone. So then you look back and say, well, what on earth do I have left here that I can use for my answer in number 25? Well, we have a 1 plus 1. That is a pretty awesome way to write 2. That is a very, very awesome way to write 2. All right, next up you have number 30, which is kind of a monster here. Okay, so whenever I see that they have things in factored form, I start to think maybe they're hiding something from me. So I would certainly go ahead and FOIL those together. And because this is a sum and difference pattern, you know, we don't have to do outside times outside and inside times inside because those are going to cancel each other out. And I get here and I think, okay, I sure do have a lot of secants going on there. If I could just get rid of that tangent squared y, so secant squared y minus, and what can I replace tangent squared y with? Well, I can use the Pythagorean identity for that, and that would be secant squared x minus 1. Oops, not x, y. And that is over secant of y. So now let's see what's going on. Let's go ahead and distribute. So it'll be secant squared y minus secant squared y plus 1 all over secant of y. Cool. Those are subtracted out of there. So I have 1 over secant of y, and I just need to figure out what is 1 over secant. Well, that's cosine. So that would be the fastest way to get to that one. Again, there's many ways to do these. It's just a matter of trying to figure out which way is the fastest way to go. Number 33. Okay, yep, I went after this one a couple of different ways, and I just found it was so much easier to just simplify this fraction first. before you do anything else. Otherwise, this gets really, really messy. So secant squared of x over tangent squared of x. And I'm thinking, well, secant is 1 over cosine, and tangent is sine over cosine, so maybe something good will come from investigating that relationship. So we've got cosine, 1 over cosine squared x, and then we have sine squared x over cosine squared x for tangent. And of course, we're going to multiply by the reciprocal, and of course, good stuff is going to happen, because the cosine squared x's cancel out. And so really that second fraction is just 1 over sine squared x. And that works out way too nice, because look at our nice common denominators here, and we will have 2 over sine squared x. And then we realize, okay, well that would be 2 times a secondary trig function, which would be 1 over sine squared x, which is cosecant squared x. So that one works out really slick as long as you change that second fraction. It just seemed very suspicious to me, you know, when you start looking at it and you're trying to figure out which way should I go with this, that we have a fraction that's made up entirely of trig functions and should be reducible. There should be something that we should be able to do with that. Then the lovely 38. So sine of x over 1 minus cosine of x plus 1 minus cosine of x all over sine of x. Well, it's a fraction. I mean, usually if we have something that's involving fractions, we're going to have to get a common denominator. So, unfortunate as it is, that means we're going to multiply the top and the bottom of the first fraction by the sine of x and get sine squared x over sine of x times 1 minus cosine of x. And I'm going to leave that in factored form in the hopes that something good will cancel out here. And then for the second one, this is where it gets kind of ugly. We're going to have to multiply by 1 minus cosine x on the top and the bottom. And so our denominator, of course, is going to be our sine of x and 1 minus cosine of x. But let's go ahead and do a little FOIL action up there on the top and see what we get. So first times first is a 1. Outside times outside is minus cosine x, but so is inside times inside. So minus 2 cosine x. Negative cosine x times negative cosine x will give us plus cosine squared x. All right, let's keep going, because now we have a common denominator. Let's see what happens. And we have sine squared x plus 1 minus 2 cosine x plus cosine squared x all over sine of x times 1 minus cosine of x. Well, in the numerator, we have these two, and that's 1. So that'll actually be 1 plus 1 minus 2 cosine of x all over sine of x times 1 minus the cosine of x. Well, 1 and 1 is 2. I think I'll factor that 2 out. Oh, good morning. There it is. 1 minus cosine x cancels out. And we have 2 over the sine of x, which, no fractions, remember, so we have to think, okay, this is going to be a 2, but if I flip 1 over sine of x, what am I going to get? Well, I'm going to get cosecant of x. And it looks like so. So there is number 38, which is beautiful. Look at that problem. Gorgeous. All right, let's see if there was another one on this page you needed, or if I can boogie on to the next one. All right, we're going to the next one. 41. Write each expression in factored form as an algebraic expression of a single trigonometric function. Okay, that sounds like fun. Let's see what we have here. All right, for number 41, what we're going to do is drop the parentheses. They're not doing anything, but maybe they are keeping you from being able to see what's going on here. Because when we drop those parentheses, we see this, which just happens to be the Pythagorean theorem, or Pythagorean identity for sine squared theta plus cosine squared theta equals 1, or cosine squared theta plus sine squared theta equals 1, when you're trying to solve it for sine squared. So 1 minus 2 sine of x plus sine squared x. And then they said we should go ahead and factor this. So this is going to be a perfect square. Now, how do I know that? Because I've got a perfect square in the front, I've got a perfect square in the back, and if I multiply 1 times sine of x and double it, I get the middle term. So this is 1 minus sine of x squared. And there it is. That's 41. 46. We have secant squared x minus secant of x plus tangent squared of x. Well, that's too many trig functions for me, and I would much rather just switch the tangent squared x than try to switch the secants, because there's 2 of those. And so I realized, wait a minute, I can use the Pythagorean identity for this one, and this will be secant squared x minus 1, which will play very nicely with our other secants. So we take a look at that and we see secant squared x, there are now 2 of those, minus secant of x minus 1. And they said to put this in factored form, so we could factor right now. I mean, we have 2 secant squared x, and we have the negative 1 in the back, and a negative 1 secant x in the middle. But some people really have trouble with this, so if you have to, do a little substitution and make secant of x equal to y. And then do your factoring. We know 2y times y will give us the 2y squared. And in the back, we're going to need a positive 1 and a negative 1. It's just a matter of placement to make sure we get a negative 1 for the middle term for negative y. So if we put a negative here, we'll have negative 2y, and the inside times inside will be plus 1y. And then all we have to do is substitute back in. So this will be 2 secant of x plus 1 times secant of x minus 1. And that's what they wanted us to do. They wanted us to put that in factored form. So that one is done. Number 47. All right, 47 says, write each expression as an algebraic expression of a single trigonometric function. Okay, well, 47, I have 1 minus sine squared x over 1 plus sine of x. And I look at that and think, wait a minute. If I use the difference of 2 squares to factor this, that will be one of its factors. That's exactly what I need to do. I need 1 minus sine of x times 1 plus the sine of x. And I have to divide all that by 1 plus the sine of x. There's my answer. So it's just one of those things where when you see a pattern, and actually looking at 47, 48, and 50, you can see that they're kind of messing with them. 50, well, 49 and 50 both take a second where you think, wait a minute, tangent squared x, I'm going to have to put secant squared x. Oh yeah, that makes sense, you know. So you think about how you can fit all of that together. 48, we're going to do the same thing. Tangent of alpha minus 1 times tangent of alpha plus 1. Difference of 2 squares pattern. 1 plus tangent of alpha. And it doesn't matter that we have tangent of alpha plus 1 and 1 plus tangent of alpha, because addition is commutative. 2 plus 3 is the same thing as 3 plus 2. So they cancel out, and we get tangent of alpha minus 1. So these are really, really about that difference of two squares pattern. So, like I said with 50, after I've done all of these, I'm thinking, oh, I don't think I want tangent squared x up there. I think I want to use the Pythagorean identity for that and say, hey, that's secant squared x minus 1 all over secant of x plus 1. And that's because secant of x plus 1 is a factor of secant squared x minus 1. Oops, too many parentheses there. And of course, we see that these are going to cancel. And there it is, secant of x minus 1. So all of those involved thinking about that difference of two squares pattern. Number 51, we have 2 cosine x sine x minus cosine x equals 0. All right, so now we're solving. Find all solutions to the equation. But this I like, between 0 and 2 pi. So we don't have to worry about making sure that we have that plus 2 pi n, where n is the integers piece. So with 51, 2 cosine of x sine x minus cosine of x equals 0. And while I'm writing it down, I notice, hey, there's a cosine x. I can factor out both of those. Okay, now, if this is 0, I have this solved. And if this is 0, I have this solved. So, this one's ready to go. I can start thinking about answers, but this one I'm going to have to add 1 to both sides and divide by 2. And now, we put on the thinking cap, 51, and we say, okay, where is the cosine of x going to be 0? Where is the x value 0 between 0 and 2 pi? And that would be right here and right here at 0, 1 and 0, negative 1. So those give us the answers of pi over 2 and 3 pi over 2. Now let's go to the second one. And that is the sine of x equals 1/2. So just think first quadrant if you don't have the unit circle memorized. And think, all right, here's my theta. Sine is opposite over hypotenuse. Oh, that's going to be 30 degrees. So that's going to be pi over 6. But that's not the only place that sine is positive on the unit circle. So you think through this for a second. Let's see, positive, negative, negative. Oh, it'd be over here. And then you have to figure out the name. If the angle is pi over 6 for this piece, what is the name for the angle with the initial side over there at 0? And that would be 5 pi over 6. And in the other two quadrants, we would be negative for sine. So we found what we needed there. And I wrote way too big, so I'm going to have to erase before I go on to the next problem. 52, we're still trying to solve, but again, we're not finding them all. We're finding those from 0 to 2 pi. So we've got square root of 2 tangent x cosine x minus tangent x equals 0. And I notice tangent x is going to come out of both of those. So we factor that little bugger out. And that means tangent of x needs to equal 0. Or the square root of 2 cosine of x minus 1 should equal 0. Well, we can think through this one right away. But this one requires a little more work. So we're going to have to add 1 to both sides and divide by the square root of 2, which we of course know is the square root of 2 over 2. Now, let's go back to the first part of this, which is that tangent x needs to equal 0. So I think, okay, how does tangent x equal 0? Well, tangent x is y over x. So when y is 0, which can only happen on the quadrantal angles, we are going to have ourselves some solutions. And y is 0 right here and right here on that unit circle. So that's going to be 0 and pi. And then we go over to the other one. And we say, all right, well, we know cosine of x is square root of 2 over 2. That's a 45-degree angle. So pretty obviously, pi over 4 is going to work for that one. And then we sit and think, okay, where else can we get cosine to be positive? Positive, 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 negative, 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 positive. Oh yeah, that's going to be fourth quadrant down there. So if I put my little pi over 4 right here, I need to come up with the name of the angle to get me there, because we have to go counterclockwise. 8 pi over 4 would be all the way around. That would be 2 pi. We need to be 1 pi short, 1 pi over 4 short of that, so that's going to be 7 pi over 4. And there it is. Number 55. 55 we have, and I think I might have squished that up here. Yes. And I think, well, I don't want that squared. I'm going to take the square root of that. So tangent of x equals plus or minus the square root of 3. And I realize that's going to take me all 4 quadrants because I have a positive and a negative tangent there. And the square root of 3 only occurs in our 30, 60, 90 triangle. And again, hopefully, you have some of these memorized, but I'm just making the drawings in case this is the stumbling block right here. So tangent, that's going to be opposite over adjacent, so square root of 3 over 1, which should be enough to tell you, hey, that's a 60-degree angle there. So this is going to be pi over 3. And then you need to go through each of the quadrants and see, okay, now if that's my reference triangle, this would be my other one over here. So that would be 2 pi over 3. And this would be my reference angle here. And that would be 1 pi, which would be 3 pi over 3, plus another pi over 3, which is 4 pi over 3. And one more reference triangle right here with our pi over 3. So all the way around would have been 6 pi over 3, but we're 1 short of that. 5 pi over 3. And you'll notice there was no division in any of these that would make it possible for us to try to divide by a 0, so that there's not going to be anything undefined here like there was in the notes. I believe that's everything.